Following on from our previous video, we are now going to use mathematics to try and understand why the gradient vector is always at 90 degrees to the tangent. So in the previous video we had some sort of surface, and if we're trying to investigate the level curve of something, we would cut it across here and put a constant into here. So in the previous video we used an example of 17. So if you cut it across here, it will then give us this level curve. So currently we've got a function driven by x and y. So if you know the x location and the y location, then you're always going to get a level. You're always going to get a level. In our case here, the level here is 17. The level here is 17. The level here is 17, and so on. So currently we are at this situation, but we are trying to investigate this tangent line. If we want to investigate this tangent line, then we should think about using our parametric equations technique, because if we can work out a way to obtain the position, so if we can work out the position vector each step of the way, then we can differentiate it. So if we know the position vector, if we differentiate the position vector, we are going to get the tangent vector. So we're here at the moment driven by the x and y location, but we want to use our parametric equations technique to force the particle to move along this path. We can do that by converting this thing into our parametric equivalence. So use parametric equations to force a particle to move along here. So now everything is driven by one variable as opposed to two. So it's driven by t. So imagine t as being time. So as time ticks away, you're always going to know the x location and the y location. You're always going to know the x location and the y location, the x location and the y location. So in effect, you know the position vector each step of the way. So later on, if we differentiate it, we are going to get this tangent vector, and we've done this before. So I'm expecting you to know this. We've done this before when we did vectors in the past. So currently, if you cut it across here, you're going to get the equation for this ellipse is given by this. So that's the equivalence to this. So now we would set up. We would use our parametric equations technique to drive everything in terms of t. So x is driven by t and y is driven by t. So as time ticks away, we always know the x location and we always know the y location. So this thing here, which is this thing here, can be written as this, as a function of this and a function of this, because we always know the x location and we always know the y location. So from here we can differentiate it with respect to t, and we've done this before using the chain rule. So we spent several videos on using the chain rule. So if you get given this situation, if you differentiate it with respect to t, then you take the partial derivative with respect to x and then times dg by dt, and take the partial derivative with respect to y and then times it by dh by dt. So we are in effect using the chain rule. So we've done this before, and I'm expecting you to know this because we've done it before. So using the chain rule, that will then take us to here, and then once you're here, once you're here, you realize that this thing here can be rewritten as a product, as the dot product, because when it comes to the dot product, this times this plus this times this. So when you're here, you realize that you can rewrite the whole thing as this thing here. And when you differentiate a constant, it will give you 0. So if you're taking the dot product of two vectors and it equals 0, then you must know that they must be at 90 degrees to each other. We've done this in the past. Whenever you take a dot product of something and it equals 0, we know that the two vectors are at 90 degrees to each other. So that means that this thing here is at 90 degrees to the tangent. Because when you get to this stage here, you know that this is you differentiating the position vector, which, well, I hope you can realize that this is your tangent vector. Okay.